What? Did Goku just use the Kamehameha? Hi, I'm Tyler Folse. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry. From engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Today we're going to be looking at a comparison video on nuclear explosion power. See which ones are the most powerful. Let's take a look. Is that a Minecraft dynamite? Kilogram taken out of car. I like all the conventional ones they're starting off with to compare it to, but this one's kind of obscure. This earthquake bomb, tall boy, I think that one was used during World War II to take out tunnels and underground structures. Kind of a precursor to a bunker buster bomb. So the Moab, it's referring to it as a thermobaric bomb. I hope that was on purpose. That is awesome. So how a thermobaric bomb works is it uses oxygen. So it sucks oxygen in, ignites it, and then just sets off this big explosion. So I guess barbaric is apt because if you're caught in one of these, it's going to suffocate you, light you on fire, and then blow you to pieces. Sounds pretty barbaric to me. Also, one thing about Moab is it's either massive ordnance airburst or mother of all bombs, depending on who you ask. There's father of all bombs. So neutron bomb says lethal side effect of radiation. Not really a side effect. So to give you a sense, I'll talk about a regular thermonuclear bomb. Those work by having conventional explosions move together a separate fissile masses of material that will fission, moves them together to where it forms a critical mass, causing fission reaction, and that is in a casing designed to increase heat, increase pressure, so it gets into the fusion stage to cause nuclear fusion, which releases even more energy and gives you that awesome destructive force. All of that process, by the way, takes on the order of a few shakes. For those of you who are new to my channel, a shake is only 10 nanoseconds, or 10 to the minus 8 seconds. So these reactions are very, very quick. Now, a neutron bomb, on the other hand, the capsule, if you will, this material is designed to either not absorb the neutrons, because the neutrons can get absorbed in there when it creates all that heat and pressure, but to even be transparent or act as a modifier to boost the number of neutrons produced from this type of fission reaction. So much that the neutrons even outrun the initial fireball from the explosion. So the end result is upwards of 10 times more neutron radiation than you would get from a typical thermonuclear bomb, which we haven't gotten to there on this chart yet because those are more powerful. But this one was developed in the 50s and 60s to take out a group of enemy tanks, and it would just kill all the drivers and the operators because they would give them much, much higher dose of neutron. But it wouldn't damage the vehicles as much because this explosion is relatively weak at 300 tons. We're not even into the kiloton range of nuclear weapons yet. But what's interesting is it's so you could just steal the enemy tanks. You just clear out their operating crews and you take them. Though I will say, back in the 50s and 60s, electronics were a lot simpler back then compared to where they are now, because I'm sure a device like this would absolutely wreck any computers, more sophisticated electronic systems that you have on modern tanks. So these things aren't used now, but not really a lethal side effect of radiation. Radiation is its primary offensive weapon, in this case of neutron bombs. Very interesting. EMP bomb. They're showing in parentheses 1 ton, but I guess one ton of materials. I've just noticed that now. They showed that with the neutron bomb as well, seeing that in the corner. 1.2 kilotons of TNT. So what's interesting about EMPs is detonating a nuke up in the atmosphere, anywhere from, say, 20 miles to, say, 200 miles or something like that, is going to cause a long-range electromagnetic pulse that can disable a lot of electrical equipment, sensitive communications equipment. So the idea is when waging a nuclear war, you take out the target country's defense systems, a lot of its satellites, a lot of its communications. So the rest of the real destructive nuclear weapons that are designed to destroy military bases, cities, infrastructure can get through without you knowing about it. But now, the effects of electromagnetic pulse, this hasn't ever really been tested on a big scale or anything like that. So there are ways to protect yourselves from EMPs, such as using Faraday cages. But this sort of thing has the potential to cause widespread blackouts, loss of power, such as with the Carrington event that happened back in the 1800s. Now, I will say 1.2 kilotons, that's not going to get you a very big EMP, even if you detonate it super high compared to, say, I'm going to say regular-sized nuclear weapon that's upwards of 100 kilotons, detonating it that high. And the altitude, the position of the target relative to the equator, and the strength of the local magnetic field can actually have just as much of an effect on the severity of the EMP as the yield. But 1.2 kilotons, that seems a little small to me. Now, it is possible for small EMP weapons that are non-nuclear, just very, very short range. But 1.2 kilotons, it's a nuke, just a relatively small one. Ooh, the Halifax Explosion. Now that's here you have a case of a tanker carrying high explosives crashing into another tanker. Yeah, you can have big yields from non-nuclear weapons. And one interesting thing about mushroom clouds, they're not restricted to just nukes. It's anything high yield. So 3 kilotons is going to get you a mushroom cloud. And the converse is also true. So those small micro nukes that you see from playing games like Fallout, it's not going to make a micro mushroom cloud. It's just going to be a relatively small explosion. There's Little Boy. And Fat Man. So they're listing using uranium and plutonium. Now that's interesting because that's accurate. Little Boy used a lot of uranium. Uranium enrichment wasn't this massive industry because the nuclear industry wasn't even really a thing yet. It was all a military thing during the Manhattan Project, and they used just about all of the uranium they had to make the Little Boy device, and they ended up using plutonium for the Fat Man device, which is one of the reasons why it was more potent. Another reason is Little Boy was not a very efficient weapon. It was very much a two-dimensional nuclear guns slide into each other kind of critical mass formation, whereas the Fat Man was a ball closing in on each other. So it gave you that extra dimension to work with. But a lot of that energy from Little Boy ended up not being used to create the fission. Another thing to point out, I mentioned thermonuclear bombs earlier. These are strictly atomic bombs or nuclear bombs. No fusion occurred in these weapons. This is just a pure fission weapon. A Cobalt Bomb. Now that one is interesting. Mentions radiation fallout worse than blast. So that's how it was designed. Another name for this is the salted nuke, because you're trying to salt the earth when using this sort of weapon. But Cobalt-60, not as radioactive as the immediate fission products that are going to be sitting around for a couple of weeks or so after the nuclear blast. Now, after that initial period of a couple of weeks, the Cobalt-60 is going to make up the vast majority of the radioactive material source. So the idea is that it'll stay there, but it's still relatively low compared to those initial fission products. But it's going to linger around for a while, on the order of years. Though Cobalt-60 does decay away faster than the long-lived fission products caused from a nuclear blast. So after a century or so, the radiation from cobalt is actually going to be less than radiation from the long-lived ones. And this one, I'm assuming you're going to go with a surface detonation, because the whole idea of a cobalt bomb is to cause as much fallout as possible. Again, using the salt the earth term. But they're not going to be... This isn't enough radiation to make the area completely uninhabitable. There were a few conspiracy theories out there about cobalt nukes completely rendering the earth uninhabitable from the amount of radiation, but it's not as much radiation as you think. The nasty part about cobalt is it's going to stick around for a while. But even still, it's not as much as the radiation from a regular 400 kiloton nuclear weapon. Looks like we skipped, don't know off the top of my head, but I believe it was 100 kilotons to maybe 150 kilotons is the largest explosion you could get using a pure fission nuke. This cobalt bomb in here is a thermonuclear weapon, fission fusion. That's how you get up into the many hundreds of kilotons or even the megatons, which I think they're going to show in a bit. That statement, radiation fallout worse than blast, 400 kilotons, you're starting to get pretty big. So this blast, again, just like I've said in my previous videos on radiation fallout being worse than the blast, it depends where you set this thing off. And it also depends on which direction the wind's blowing. So that's not necessarily true even with a cobalt weapon. But it could be. That's what it was designed for. Another weird weapon, kind of like the Neutron Bomb. Here we go. B-83, deadliest one actively used. We're in megatons. Castle Bravo. So now we are getting into the era of the big booms. That's a technical term. Not really. But this is kind of when the doctrine was around, let's set off really big nuclear bombs as opposed to overwhelming a country's defenses with a bunch of small but still deadly on the order of 400 to 800 kilotons. But these things were big. That Castle Bravo says largest detonated, B-41 made a 25 megatons just to make them even bigger, but that one was never actually tested. Yeah, just a different era in terms of nuclear warfare. A lot of these were had to be carried by big bombers, though, which is part of their weakness. Very, very easy to intercept, as opposed to the idea of an intercontinental ballistic missile carrying a bunch of small warheads, splitting at high altitude, and doing moderately severe damage to 6 or so cities instead of very severe damage to just one. Ah, the SAR bomber. That's the biggest one. So, okay. So here they showed the 50 megatons, which is the detonation one. That one, you could scale it up to 100 megatons, but they didn't want to detonate one that big because the bomber wouldn't have been able to reach minimum safe distance. That weapon right there is the epitome of the big boom era, and that one in particular was really just a propaganda weapon. It would have been impractical to use in a real nuclear war because it had to be carried on this big lumbering bomber, and the bomb was so big it wouldn't actually fit in the bombing bay doors. It would have made it so easy to get picked up on radar, and interceptors would head out and shoot it down. But it was more of the Soviets saying, hey, we can build this really big bomb. Our nuclear weapons technology is so far superior to the Americans. Nature is far, far deadlier. Volcanoes. All nukes detonated together. This one shows up a lot in a lot of my videos. Let's see, this video is a few years old actually, but yeah, 7,000 megatons. That's a lot. I actually think our number is smaller now than it was in 2017 for all the nuclear bombs combined. One other thing is that would create a lot of careful timing in order to actually do that sort of thing, rather than having one nuke just destroy the other nukes without getting them to detonate. But it can be done. It's not impossible to pull off a crazy experiment like that. What, earthquake? What? Oh, that's funny. It's purple. Purple antimatter. 1 ton of antimatter. Wow. For a substance that costs trillions of dollars per gram. So, ton, million grams, so quintillions of dollars to synthesize that much antimatter. You're better off just building even more conventional nukes to create something like that. But antimatter is interesting because that's when you're using all of the E equals mc squared. All these other nuclear reactions we've been talking about, fission or fusion, has been delta mc squared, the change in mass energy from causing these nuclear reactions. But this, you get the full thing. But it's very expensive. We need to wait for the cost to come down on something like that a lot. Not sure if it'd be purple though, but it's pretty. Super volcano eruption. Okay, it's like he's done a few calculations on super volcanoes. The eruption will be visible from space. Sure? I like this cheesy graphic, it's pretty good. Deadliest explosion, Earth, outer space. So one thing about volcanoes is the whole nuclear winter, impact winter, volcanoes are better at that than nuclear weapons. Even if for nuclear weapons with equivalent yield to that super volcano, if we somehow built enough, because they spit up so much sulfur dioxide, so they're going to create that whole global cooling effect, because that lingers in the upper atmosphere. Whereas nuclear weapons are really just really, really big forest fires in terms of what lingers in the upper atmosphere that would cause that sort of winter effect. I'm not saying they don't cause anything, but the effects of nuclear winter, pretty exaggerated relative to what was once thought back in the 80s. But volcanoes can actually have more of an effect, and asteroid impacts, looks like we're getting into that next because it says outer space decides to play a game. Asteroid that killed the dinosaurs. These old crackly sound effects. That is a lot more powerful. I like that he's talking more about these than the actual nukes. It really puts the strength of nukes into perspective Earth has ever witnessed. Is it, though, for now? What? Did Goku just use the Kamehameha? What is this? Death Star? Gamma ray burst! Okay. By the hypernova of a nearby star, everything is way will vaporize. Okay, a couple of things. One, I think he missed out on including the Theia impact when Earth collided with a Mars-sized object 4.5 billion years ago. Now that one's a little out there in that the jury's still out over whether or not that actually happened, because this sort of thing was like, hey, this also created the moon, responsible for Earth's axial tilt. Let me know what you think of that that impact theory from 4.5 billion years ago. That one, there's still a bit of debate over that origin, but that would have been way more deadly than the asteroid that killed the dinosaurs if, well, I use the term deadly, nothing was alive on Earth at the time. This was deep in the Hadean eon, when Earth was very hot, but that was a bigger explosion. Now on to the gamma ray bursts. Gamma ray bursts are quite powerful. Let me see if he says more about it. 1 nonillion tons of TNT. Oh, that's great. So gamma ray bursts, well, what he showed there looked like a bullseye, a direct hit, and he said hypernova of nearby star. I mean, sure, if like Alpha Centauri had the star that was capable of going hypernova, then yeah, the Earth's not surviving that. It's going to be completely destroyed. Maybe even the hypernova by itself will do it, let alone the gamma ray burst when you're just a few light years away. So gamma ray bursts, they do have the potential to do that. They don't even have to come close to Earth to, well, that close to Earth. They can come within a few thousand light years of Earth, and Earth might actually be all right. But once you get into the few hundreds of light years, it can start to mess with the upper atmosphere, take away the ozone layer, do all kinds of nasty stuff like that. Fortunately, there are no solar systems close to ours that have stars with that potential to go hypernova, or neutron stars combining to create a kilonova, all these other types of novas that are out there. But yeah, we're relatively safe, despite it being a relatively common occurrence in a galaxy. We're in the part of the galaxy where there's not a whole lot of gamma ray bursts that are within range to cause damage to Earth. So this sort of thing, I think we're pretty safe from. His hypothetical scenario of a nearby hypernova, yeah, that'll destroy the Earth. This was a fun video. I liked that it didn't take itself too seriously, such as the Thermobaric. Hey, if you like this video and you like peaceful uses of nuclear energy, please join me on my journey to a clean, safe, sustainable nuclear energy future by liking, subscribing, and commenting if you haven't done so already. Thank you very much for watching. I'll see you next time.